Assalamualaikum warahmatullahi wabarakatuh. Class, can you see the slide?
Yes, doctor.
Okay. Okay, so let us start today our class. Okay. So today we will continue with lecture 13b. I think last time we stopped at the question for for the next example. So this time we will continue with the solutions and proceed with the transients response analysis. Okay, so let us recap regarding transient response. Okay, the transient response of a dynamic system is closely related to the location of the poles. Poles we learned previously, poles located on the right side of S-plane will result with unstable system. So this one you learn during topics on stability. And all poles are negative real numbers. The output will be overdamped. A complex conjugate poles, a damped oscillating system, and finally poles on imaginary axis results in sustained oscillations. So let us look at the figure that describe the conditions of um, all the things that we described earlier. Whenever the locations of the poles, where the location of the poles is, so in this S-plane, we have 4 quadrants, okay? And the first one, positive real roots increasing without boundary. These are 2, the quadrant number 1, let's say this one is 1, and then this is 2, okay, 1, and then 2, and then 3, 4. Okay, so the quadrant number 1, positive real roots increasing without boundary. We know that it is at this is for unstable system. So here, unstable right side of S-plane. And then stable left side of S-plane. Then the number 2, when we have complex conjugate pair. And then number 3, negative roots, real roots, exponential decay. And finally, quadrant number 4, complex conjugate pair of roots, positive real parts, growing oscillations. Okay, this is the transient. And then we also learn about determination of the damping ratio, and then the um, natural frequency, damp and undamp, and then also the time constant from the root locus that we sketched during our previous lecture. And then this time we will concentrate on looking at for this time this one, okay, mostly it is on the transient response, and this one is actually at the steady state error phase. So here, if you look, this is the the position, the condition. This one is the transients, the one that we try to find it, try to find what are the settling time, peak time, and then this part is the steady state response analysis. So from this root locus, we can find the settling time, the peak time, and the steady state error. Okay, if we have the condition, okay, for system design, then we can set the locations for the design. Okay, so we proceed with the there is noise. Okay, so we proceed the one that we stopped during our last lecture, and this is example 8.8, third order system gain design. This one is from NICE, NICE control system textbooks. Okay, so we have considered the system shown here in the block diagram, feedback control system. For example 8.8. Okay, so where we have the transfer function is k s plus 1.5 over s plus 1 s plus 10. Okay, now what we have to do is design the value of k to yield 1.5% overshoot, and then estimate the settling time, the peak time, and the steady state error for this system. Okay. Okay, so let us start. Have you tried to sketch the root locus for this example class using all the 9 steps or all the 9 rules of root locus? Tidak. Okay, let us try to do that. So we have 1 zeros and 3 poles. So for step 1, okay, number of poles, number of zeros. So number of poles here 3, where we have P1 is 0, P2 minus 1, and then P3, P3 minus 10. And then we have 1 zeros, Z1 equal to minus 1.5. So on real axis, loci are on the left of the odd numbers. So let us try to draw that. So we have P1 here, negative 1. We have P2 here, and then we have negative 10, P3, P3 here, and then somewhere here 1.5, we have Z1. So it says here we should have the locus at the odd 1, 2, 3. So in other words, it should be something like this. Okay. And number 3, we proceed with number 3. Number of root locus is equal to number of poles. So in this case, we have 3 poles. So where this one, we have 3 root locus. Okay, so 3 poles. The first one start P1, the second one start at P2, and the third one start at P3. Okay, so the first one, if you look, this one. Okay, let's say I use red for this one. And then we have P2, the blue one. Okay, and then we have the P3. Yeah? Okay. Okay, so P1 ends at Z. So one of the poles will end at the zeros, and the rest two will end at infinity. Okay. So we proceed with step number 4. Stop me class if you don't understand any of the topics that I discussed here. Okay, the asymptote angle. So since we have D is actually number of poles minus number of zeros. So we have 3 poles, 1 0, so it will be 2. Therefore, our asymptote angle is 90 and 270 degrees. And then we proceed with step 5, finding the center of asymptote. Okay, so PG summation of PI minus summation of zeros over D. Then we have the point is minus 4.75. And then we proceed with steps number 6, which is breakaway point. So let's say we use method number 1. Okay, so I'm using method number 1. The first one is 1 over breakaway minus our P1, P2, and P3 equal to 1 over breakaway minus Z1. Okay, so we have this when we solve. Okay, we have this equation. Now, how do we get to find the roots? So in this case, we have three third order systems. So therefore, our roots will be 3. So solving this one using polynomial, or you can try to use, I'm not sure today. Today, if times permit, we will do the MATLAB for control system. So we try to use, you can also find the roots using MATLAB, the one we will learn later today. So in this case, we have the breakaway point. There are 3, minus 0.621, and then minus 2.7682, and finally minus 4.3604. Okay, so we proceed with that. So step 7, definitely our locus will leave or approach the real axis. So make sure that when they leave or approach, it is at a straight line. Okay, so must be straight line during axis, real axis. And then the angle, the locus leave a complex conjugate. Since we don't have a complex conjugate open poles, so therefore it is not applicable. And then the intersection of locus with imaginary axis, so we don't have intersection at the imaginary axis. Therefore, step number 9 also not applicable. Okay, so based on all the information that we have here, step number 1 until step number 7. So we plot that. So I'm for the easier demonstration, I'm sharing you the results, the root locus using MATLAB that we're going to learn today, hopefully. Okay, so this is our root locus. So this is P1, and then this is P2, and then this is Z1, and then this is P3. Okay, and then we learned that the asymptote angle about 4 point just now, 90 and 270, 4.75, somewhere here. Okay, so let's say this is 5, 4.75 somewhere here. So this is our asymptote. Okay, so step number 4 and number 5. And then step number 6, the breakaway point, 0.62. So I'm putting sigma here. So here, somewhere here, this is breakaway number 1. Somewhere here is breakaway number 2, 2.7 kan. Okay, so somewhere here is breakaway number 2. Then here, somewhere here for something tadi kan, 4.3. So this is breakaway number 3. So up until here, are you okay, class? Okay, so root locus number 1 start at start P1 equal to 0. Okay, so blue, yang ni blue. So they start at 0, and then the breakaway, then the end at Z1 tadi equal to minus 1.5. Betul? And then root locus number 2, green, yes, green. The start P1 equal to minus 1, this one. Green, tak ada lah green. Tak apa, so green this one, ini green. And then the start, the break sama, break at breakaway number 1 tadi apa number point tu? 0.6213. minus 0.62. Okay, so it breaks here and then it will go to breakaway number 2. Okay, sini number 2 and then here goes to infinity. And then root locus number 3, it is red. Okay, start at P3 here, and then it breaks at breakaway number 3, then it goes down to infinity. We start at P2 lah. It's P2, this one is P3 minus 10, and infinity. Okay, so far class, so good. So actually we are reviewing the root locus steps before we proceed with the design dia tadi apa steady state error. Okay. The question is actually design the value of K to yield 1.52 overshoots, and we have to find the settling time, the peak time, and the steady state error. So we still at the root locus design. So this is the root locus. Any questions so far on the root locus itself before we proceed with the design part? Okay. So meaning if no question means you understand everything. Okay, no so let's okay. Yes, no Ati?
No question, no question.
So very clear that I'm explaining it clearly.
Doctor, I want to ask.
Okay, too.
Why the root locus is circling around the 0?
Circling the 0. Actually,
yes.
which one? The blue one, the green one, the red one?
The blue one and the green one.
The blue one and the green one. Okay. The blue one is root locus number 1. Okay. Yang ni mana point dia? This one P1. And then it will break. Satu dia ada satu. One is the P1 and another one is the P2 at minus 1. Okay. Minus 1, 0. And it will break. Because we don't have anything outside the unstable part. So everything when we try to sketch just now, it says that somewhere here and then somewhere here kan. Okay, so here it will break, okay, because there is 1 0, so the poles must end at zeros lah. So dia pergi sini and the break dia pergi zeros. Okay, but the other one, okay, the break again, it will go to infinity.
Oh, okay.
Okay,
I
so
understand
this is the second one, they go to infinity. And then the third one sama, they break dekat at the point breakaway number 3, they go to infinity. Number 2 tadi, because there is 2 breakaway point, 3 lah actually, for 2 for P1 and P2. One is at berapa tadi kan, 0.62 and another one is 2 point something tadi kan. Okay. Answer the question tu? Boleh
clear.
Okay, so now because the design mentioned about percent, we have to determine the value of K with overshoot is about 1.52. You still remember the transient response? So kalau kita ada step input, let's say step input. Okay, so our response for the second order system adalah macam ini kan. Okay, so dia kata overshoot is kat sini lah. Okay, so overshoot here is given at 1.52, tak silap saya tadi, 1.52%. So using these equations, we have percent, I assume you learn this formula with Dr. Sanius. So percent overshoots equal to e to the power, the rest of the equations. So therefore, using the condition of the overshoot, which is 1.52 or 0.0152, we put that into this equation. Therefore, our damping ratio is actually 0.8. Okay, now applying this damping ratio 0.8 to our previous root locus, okay, this one that we sketched earlier. Okay, so this is the damping ratio to satisfy the condition of overshoot 1.52%. Okay, so this one. Okay, so design the value of K to yield 1.52% overshoot, which corresponds to damping ratio of 0.8. How do we manage that? Previous formula, yani. Okay, this one. Percent overshoot is given as here. Okay, when we draw this one, so using, if you are doing it graphically, so 0.8 lebih kurang berapa sudut dia? Plus beta inverse cos kan? Inverse cos 0.8 lebih kurang berapa? Can someone calculate for me? Sudut dia berapa untuk kita draw ni? No. Class? 60%? 60 degrees? Do you know how to calculate beta tak?
Is it inverse cos? Inverse cos 0.8 is equal to 0.8 or in radian.
We want to draw that. Let's say this is this one graphically lah, because exam you have to do it graphically. Okay. So berapa persen? Siapa yang mention tadi? Tu lah tu calculate tu. Ati calculate untuk saya, Ati. Yang lain ni pemalu. Hello? Hey.
Calculating betul ada.
Lama je nak calculate. Anyone can give me, anyone, tak kisahlah Ati ke tu ke tu ke.
I calculate in
Berapa?
okay.
Hello? Berapa? Someone answering just now?
I guess Siti is answering. Is that
Beta ke doktor?
Beta, yes, beta.
36.87.
36. Okay, so kita letak je lah. Assuming that is the
36 Dr. 37.
36.7 degrees, okay. So you
37 Dr.
36.7, 37, it's okay lah. Sebab ni because doing it graphically, usually the values tu dia memang lari lah. So we find the beta and then we draw it here, and then the value of K depends on the point that correspond ataupun or intersect with our root locus. Okay, so okay, so this one the answer is using MATLAB. So we find it there are 3 points correspond to the condition of maximum overshoot of 1.52. Okay, so when we draw this 0.8 line here, okay, based on beta 36.7 degrees, so we have point, the one that I put it here. So S1, this is S1, this is S2, and this is S3. So this S3 intersects with the root locus. So we have the first one is here. So let's say we concentrate on the positive side only. So S1 is minus 0.87 plus J 0.66. And then we have S2. Okay, so S2 yang ni. And then we have S3 yang ni. Okay, this one S3. Okay, so up until now, class, can you follow me? Okay, let me proceed.
Yes, doctor. Can, doctor.
Okay. So because we want, the question is design the value of K to yield 1.5% overshoot. Okay, so what are the values of K? So let's say we choose for S1. Okay, remember the characteristic equation 1 plus KGHS equal to 0. So K will be negative 1 over GHS. And then if we want to determine the magnitude, so it will be 1 over GHS. Okay, so in our case, GHS, our K will be uh, 1 over, so therefore yang apa tu? S plus 1, S plus 10. Kita ada zeros, so S plus 1.5. Okay. So this is K. For in this case, there are the zeros, the 3 poles. So let us calculate, because this means that we need to determine the distance. When we have this one magnitude, finding the magnitude of that is actually the distance of that point to the poles and the zeros. Okay, please look at the okay. Okay, here. So let's say this is our point S. Ni. Okay, point S ni saya besarkanlah this part. This part. Okay, so our S1 just now, the coordinate is minus 0.87 and then the Y is 0.66. So now we want to determine the distance of that point to the post. So post number 1 here, and then post number 2 here, and then this is zeros, and then post number 3. Okay, so you can do that for during the final. Final memang adalah soalan bentuk macam ni, soalan bocor. Okay, so in order for you to do that, sebab you have to do it graphically, so you can measure lah. So from your graph, so you kira lah, measure pembaris 1 point here, distance, 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 distance. Okay, so measure using your ruler. Remember, don't forget the scale that you used last time kita discuss. Kalau scale, if you use 0.5, so later you have 2 times 2. Okay, so if you're doing it by calculations, so boleh tengoklah kat sini, kan? So maknanya S tu square root of Y X. Okay, so this one is by calculations. Okay, by calculation 0.87 square plus 0.66 square. Sini, this is 0.66. This is 0.87. And then S plus 1 sama and all that. And then we put the values to our K formula, which is mana tadi? All the distance of poles ni. All the distance of poles divided by the distance of zeros. Mana value saya lain ni? Berapa tu? 0.63, 9.12. Oh, ni silap So please, this one change 0.912. Okay, here, this is the correct answer. Okay, so you have K is 7.37. And then, so far here, okay tak? Okay, silence means you understand. Okay, and then we proceed with the question asked about settling time, peak time dengan steady state error. All these things that you learn, the formula, all the formula here is actually from the topics on transient response last time. So putting all the values of theta, omega n and all that. So these are the value for PS for this point for the first S1. Kita ada 3 tadi. 1, 2, 1, 2, 3. So I'm showing you only the S1. So please try for the rest, S2 and S3. Okay. So the peak time, the settling time, the peak time and the steady state error. Okay. So actually the textbooks it shows all the answers for the 3 different cases, point 1, point 2 and point 3. Yeah. So these are the different values for gain, settling time, peak time, and the last one is actually for steady state error. Okay. Ada soalan? Okay, so I proceed with the response. So this one ni for your additional knowledge lah. So this is the response. Kalau kita tengok the response for different values for different cases, it will affect on the, because kita tahu kalau settling time, peak time, settling time to show how fast the system's response and settle, and the peak time also telling how fast the system responds to the input. Okay. Okay, so I think that's it about lecture 13A. Any question? Senyap, adakah anda faham? Hello class? Trying to absorb.
Doctor, how we determine the closed loop host already?
The 3 points now.
Yes.
Tanya bahagian mana How do you get the 3 points?
S1.
S1, S2, S3 tadi.
Yes. If we drawing not so good.
Okay, this one can you this one tadi kita dapat beta. Condition dia adalah because the condition it says here dia tak direct lah, dia give the overshoots and then kita convert into the damping ratio. So damping ratio kita draw the line. Damping ratio ni is actually telling us the degrees lah. So we draw the line graphically kalau you all buat ni soalan final lebih kurang macam ni lah. Okay. So you draw the line for the damping ratio and then nanti then you will get the points that intersects. Okay, this is the one the closed loop post lah. Okay. This is the one that we will find the points that intersect with our root locus. Sebab root locus dalam case kita sini, root locus here has been colored with blue lah. Tadi kita buat just now. Ni. This one close. Then dia buatlah somewhere here dia punya damping ratio tu. Situ. Okay, this one ni apa tu? So I padamkan balik semula lah. So you already understand this part tu. Kan? And then kita kata tadi apa damping ratio. Punya tangan ni macam 30 about. Ni ada pun ni. 0.8. Berapa tadi? 0.8 somewhere kan? Inilah. 0.8. Yang dia akan dapat point tu. So kalau dalam MATLAB nanti kita belajar. Tadi tak payah convert pada degree lah. So these are the 3 points lah tadi. That's one, the open, the closed loop poles. Okay, tu.
Okay, if our drawing not so good, like.
Drawing, itulah kena kalau masa apa buat graf nanti kena buat betul-betul lah. Okay, so lebih kurang. Tapi kat sini dia buat cantik je lah, bulat kan. Okay, sebab bulat tu because of the scale lah. Di scale ni dia besar, dia getting it lebar to the x-axis. Dia jadi lebar macam tu. Okay, kalau dalam buku ni mungkin dia gunakan the same scale, I don't know, I'm not sure. So dia jadi bulat cantik lah ni. Okay, so once you have the 3 points tadi, okay, the 3 points, the open, the closed loop poles, this one, the S1, S2, S3, okay, nanti you tengoklah point dia apa, you have to determine lah the point. So you know the X and the axis. So I'm giving you the answer. So these are the points 3. Okay, because once we have the points, the closed loop poles, we have to determine apa dia minta. Ada K, and then the settling time, the peak time, and then the steady state error, kan? So I'm showing only in this lecture notes, I'm showing only for S1 lah. So you can try proceed with S2 and S3 because the whole answer is given here in table 8.4. Okay, so for this is for second case, second point, third point, and these are the one that we have to calculate the gain, the settling time, peak time, steady state error. Okay, am I answer your question too? Boleh tak? What about others? Any more questions on this topic?
No, doctor.
Ada. Okay. I'm not sure whether I will do the MATLAB or the design. Okay. Okay, so this one habis. Stop presenting. If you look, this is for anyone tak sempat nak slide in, kalau boleh slide, you can slide in using the one that I insert in e-learning. So dalam e-learning saya letak juga lecture 14a, I also letak MATLAB for control system. I think I would rather discuss on this one. Okay. MATLAB for control engineering, because because for the next part, the last part of the lecture is engineering design control, engineering design. So we will use MATLAB to determine the K and then on the damping ratio and so forth. Okay. I need you to go to, can you see my screen, class?
Yes, Doctor.
Yes, doctor.
So I have to share this one with the class ni lah sebab ada section lain kan. Okay, jap. Okay, now class, can you go to MATLAB online? Please log in, kalau siapa tak ada account lagi,